our final project, we decided to use CFD simulation using Star CCM Plus to optimize the full aerodynamic package of our 2019 FSAE car. We import the body, wheels, driver, and engine from SolidWorks into Star CCM. Some components are designed on Star to reduce iteration time. These include the front wing, rear wing, and diffuser. For example, front wing element 6 angle of attack can be adjusted by changing a value, the CAD updated, the mesh updated, and the simulation run again. A block is defined to represent the wind tunnel. Unite and subtract tool is used to create a negative of the car model. The inlet, outlet, ground, and symmetry planes are defined under the regions tab. The inlet is defined at 50 miles per hour, which is the average speed around an FSAE track. An open road simulation requires moving floor and rotating wheels, so the floor shear stress is defined as slip and both the wheels with a rotational velocity of 110 radians per second. 3 different types of meshes are used: surface mesher, trim cell mesher, and prism layer mesher. For the default controls, the base size for each cell is changed to 0.05 meters with 3 prism layers, and everything else is kept at default. For the mesh refinement, we refine mesh on areas that produce aerodynamic downforce and areas in which divergence can occur. These include the chassis, the diffuser, the wings, the winglets, and the tire wake. The mesh refinement can be checked using the Y+ value, which represents the mesh quality in relation to Y+. Star CCM has a built-in scalar plot for the Y+ value. The scale is set at a range of 0 to 10, which is what we want the Y+ value of the mesh to be in order to be accurate. The mesh looks to be sufficient in most of the aerodynamic components. The solvers include steady state, partitioning, wall distance, segregated flow, k-omega turbulence, and k-omega turbulent viscosity. Center of pressure is a value that determines the stability of a vehicle. We like to have the center of pressure behind the center of gravity because at higher speeds the front wing will produce more downforce. So to prevent high speed instability, we move the center of pressure behind the center of gravity. The center of pressure is calculated using the built-in function on Star. The values are then outputted and a part is derived, not needing to repeat the calculations every time. For iteration 1, the parameters are all pictured below. You have 6 different parameters for each airfoil pictured below. Here are the front wing parameters, here are the rear wing parameters, and here are the results of the calculations. This combination makes 2.723 coefficient of lift and 1.248 coefficient of drag. Iteration 2 is used to verify the benefits of rear wing 5 and if it can be removed to save manufacturing time. The front wing parameters are all the same. The rear wing changes slightly with rear wing 5 removed. The results show the coefficient of lift does increase slightly due to the decrease in frontal area, but more importantly, the rear wing downforce value drops by 8 pounds and the center of pressure moves 0.04 meters forward in the wrong direction, verifying the need for the 5th element. By iteration 5, the COP is still not in ideal position and no additional downforce can be generated with the rear wing. Elements from the front wing need to be removed. The front wing element 7 is removed and all other parameters are kept constant. The results show that the removal of the front wing 7 does reduce the amount of downforce created by the front wing by 7 pounds. The center of pressure is now in a better position, 4 centimeters behind the center of gravity. With the CFD done, we now determine if the front wing can withstand the downforce it creates. We estimate that at a max speed of 100 miles per hour, we generate 200 pounds on the front wing alone. We model the front half only due to symmetry with spars and ribs fixed at 3 mounting points and 100 pounds over the center of pressure of that airfoil. The part is nowhere near to yielding and has a factor of safety over 5, but this was needed in order to keep the deflection under 1 millimeter. The added factor of safety is also nice in case any cones decide to jump out of nowhere.